Hey guys, we're still in chapter 9, and what we're doing is we're finishing up the chapter looking at certain types of functions, particularly linear and nonlinear. This section, we're only going to talk about what's linear and what's not nonlinear, but we're not going to talk about the specifics of nonlinear functions, and we'll do that in sections that are coming up. So this is really just say, hey, are you linear or are you not linear? That's all we're doing. So let's take a look at our first thing, which is our vocabulary word. Our vocabulary word today is nonlinear function. That's pretty big. What we're going to do is discuss a little bit about what a nonlinear function is. And a nonlinear function, as you would think, I'm going to see if I can change the way I'm going to do this. A nonlinear function, I'm going to have to type it in there, I think. A nonlinear function is a function that when you graph it, right, when you graph the function or the ordered pairs that make up the function, you won't get a line. All right, so that's basically what a nonlinear function is, and we're going to look at some examples and some characteristics so we can actually determine what we have. Let's get started. So in this example here, example 1, what we see we have is that we've got several different graphs, and we're going to determine if it's linear or not. So you get that this is kind of easy because here we have a line, and that's linear. One trick also about linear equations that I want you to see is that all linear equations can be written in the form y equals mx plus b. This is something we should have talked about before, where m is the slope and b is considered the y-intercept. Another form of a line that we can always write an equation, a linear equation in, is ax plus by equals c, where a, b, and c are integers. And we remember that integers are negative and positive whole numbers, all right? So anytime you see an equation that is written in either of these two forms or can be written in either of these two forms, you know you have a linear equation. I know I said a lot for you to just look at this and say, well, it's a line and it's linear. So yes, this is a linear equation. It's a linear equation because it forms a line. I want you to look at this. This is not a straight line. It is not a curvy line because that doesn't make sense. A line is straight. So when you say line, you're talking about something straight. When you see something curved, it is a curve. This is certainly a curve. So this is not linear or non-linear. All right, over here you notice that this equation has an x to the third power, which is not a part of either of our linear equation situations. So I'm going to scooch down here and look at this next one. Here again we've got a curve. This curve is called a parabola. I don't know if you guys remember that term before, but you've heard it before. This is called a parabola, and we have negative x squared plus 5. X squared is a tip-off that this is not going to be a linear equation. Clearly this is non-linear. And the next example is again a curve. It's a beautiful curve, but x is interesting. If you notice, x is in the denominator. What that means is that x is not to the first power. It's actually x to the negative 1 power. If you remember how negative exponents make numbers go into the denominator, it will be clear to realize that the exponent there is negative 1. So indeed, in this situation, we know that this is also a non-linear function. Pretty simple, right? So that's easy to do once you have the graph. Now, if we don't have the graph, as we're going to see in example 2, we can actually just have an equation. Now, do you remember what we talked about just now? We said that a linear equation can be written in two forms, at least two forms, but two forms that we'll talk about. This is called standard form, ax plus by is equal to c, or this one, y equals mx plus b, where m is the slope and b is the y-intercept. Look at this equation. Can you manipulate it so it looks like this? I think you can, right? So what I'm going to do is I'm going to solve for y. Y is equal to, subtract 3x from both sides. When I do that, y is equal to negative 3x plus 7. Some of you are saying, Dion, you didn't have to do that. And you're right, because notice this equation was already in standard form. This is certainly a linear equation. You can say that with confidence. Oops. Let's go ahead and fix that. All right, so you can say that with confidence. Let's look at this guy over here. Do you see this exponent of 2? This is reminiscent, right, of this one right here, this equation here. We said that this shape was a, do you remember? This shape is a parabola, right? And we get that anytime we deal with a certain type of equation called a quadratic. This is actually a quadratic equation because of that too. And that lets me know that this is nonlinear. A really easy way of saying that it's nonlinear is saying, hey, there is nothing I can do to force this equation into this form or into this form. Let's go ahead and take a look at our third example. Here in example 3, we are not looking at equations, nor are we looking at graphs, but we're actually looking at tables. So when we look at tables, there's something specific that we need to check. We need to look for the rate of change, right? Rate of change we talked about, it really reminds us of the concept of slope. So we're thinking about the change in y over the change in x. Here's the key. Anytime, for any two pairs of points that you have, the change in y over the change in x must be consistent. So we're just going to check it out. So the best way to handle these is to take a look at the change in y. Check out the change in y. Here I'm going from 1 to 2. That change is 1. From 2 to 3, change is 1. 3 to 4, you got it, change is 1. Let's make sure that we have the same consistency with the change of x. So as I go from 2 to 4, that's a going up by 2, or positive 2 change. Another positive 2 change as we go from 4 to 6. And another positive 2 change as we go from 6 to 8. Notice that the rate of change is going to be the same. 1 over 2, 1 over 2, 1 over 2. Even if we were inconsistent and we jumped from the first set or the first pair of ordered pairs to the last pair, I'd get a change of 1 to 4, which is 3. Look at this change from 2 to 8. What's that change? It's going to be 6. What is 3 over 6? It's going to be the same as 1 over 2 as we had before. So we can see that this is a linear equation. Specifically, it's a linear equation with a slope of 1/2. And we can do that for each of these tables. Let's take a look at this one. From 1 to 4, we get a change of 3. From 4 to 9, we get a change of 5. From 9 to 16, we have a change of 7. This doesn't tell me already that we don't have a linear equation. Remember, you're comparing the change in y over the change in x. So let's check out the change in x. The change in x looks consistent, right? We're just going up 1, so it's a positive 1 each time. This consistency in the x and this changing in the y tells me instantly that I do not have a linear equation because the rate of change isn't consistent. I don't have a slope, per se, for all of these points to fall on the same line. Does that make sense? I hope so. Let's look at the next couple of examples. If we look at the change here, we're going from, the change here is actually a negative 15, so we're dropping by 15. The change from here to here is negative 25, and the change from here to here is negative 35. Again, this does not automatically indicate that we don't have a linear equation. We need to check out the other side. For 1 to 2 is a change of going up 1. We've got going up 1 here and going up 1 here. Obviously, 15 over 1 does not equal negative 15 over 1 doesn't equal negative 25 over 1, doesn't equal negative 35 over 1. So again, we have nonlinear equation. So nonlinear here and nonlinear over, no, this one was nonlinear. And we're going to check our last one. So 10 to 14 is going to give us a jump of 4. 14 to 18 gives us another jump of 4, and here we've got another jump of 4. So we've moved up positive 4. That's been the change in each of those y values. The change in my x values are positive 3 here, positive 3 here, and positive 3 here. Notice the consistency here and here doesn't matter until we put them over top of each other. So 4/3 in each case is going to tell me that I indeed have a linear equation. And I think that's enough for us today. Please let me know if you have any questions. I look forward to talking to you soon. Have a good day, guys. Bye-bye.